we present a global max flow-based multi-resolution next best view method for reconstruction of 3D unknown objects. A complete 3D model is essential for many autonomous applications such as crop monitoring and grasping. In this work, we focus on the active reconstruction task based on a robotic arm with an RGBD camera to perform automatic 3D modeling of a previously unknown object. The key to active reconstruction is the use of the next best view planning method. The goal is to find the optimal view that covers the largest current missing surfaces of the object. This video clip shows an example of the next best view. Based on the current reconstructed surfaces, the system infers that the surface on the other side of the object is missing and guides the robot arm to that view to collect data. Facing an unknown environment, our system reasons from uncertainty. We use Octomap to represent the information of 3D space and randomly sample candidate views. The ray casting process can evaluate each candidate view, which calculates how much new information is gained along those rays. Among them, the resolution of the Octomap and the ray sampling interval affect the acquisition of information. Small unknown voxels of higher resolution may be merged with surrounding voxels of lower resolution. Thus, some information is lost. Also, the high resolution requires more rays to hit small voxels. To balance the precision and speed, we propose a multi-resolution strategy to increase the resolution from low to high. Different types of voxels have different amounts of information. Invisible voxels and those too far from the current object surfaces should have a lower amount of information. The predicted object surfaces are determined based on the distance to the nearest 6 frontier voxels. In summary, the next best view is chosen by the largest sum of weighted volumetric information of the voxels traversed by the sampled rays. However, such a next best view planning method greedily considers the largest current information gain. As a result, some surface details will eventually be missing, such as the gray voxels in the last column of the figure. This is due to the fact that in some cases the local greedy method will stick to the local optimum, as shown by the selection of similar or the same views on the left. Therefore, we introduce global knowledge to improve this problem. The global solution of 3D modeling can be regarded as finding the smallest view subset that covers all surface voxels. As shown on the right, fewer views and fewer surface intersections. However, the view subset can be solved by the set covering optimization problem when given a prior 3D model. In an unknown environment, such an NP-hard solution is clearly not applicable. Therefore, we change the objective from the minimum number of views to the one that covers the maximum amount of information. We constructed a view ray voxel tripartite graph and placed the corresponding information on the edges. Here is an example of using 2 views to cover 4 voxels with the maximum amount of information. To solve this optimization on the graph, we model it by the network flow. By adding a source, a sink, and a capacity of each edge, we can solve it by a minimum cost maximum flow algorithm. In addition, solving this flow model is in linear time complexity. Next, we designed the information gain function based on the traits of the network flow. Each voxel finds its own optimal view by its flow, but it will have multiple optimal views and one of them will be randomly obtained by its flow. Therefore, we assume that the previously solved subset of views also contains certain information gain, and their contribution rapidly diminishes as the iterations progress. Finally, we choose the next best view by considering a combination of local and flow information gains. To verify the performance of global next best view planning, we conducted reconstruction experiments on some object models. Our code implementation can be found on GitHub. Simulation experiments show that our method can ultimately achieve higher coverage and lower uncertainty than other baselines. Experiments in a real-world environment also confirm that our global next best view planning captures more surface details. In addition, we found that those views with short distances to the visited views are planned in the following iterations. This is reasonable because the maximum missing area is captured for each iteration. However, this will considerably increase the cost of robot motion. Therefore, it is interesting to find a better view evaluation that reduces the cost of motion and ensures sufficient surface coverage. A possible solution is to find a set of next best views by maximum flow for each iteration so that we can plan the global path between these views. Thank you.